I swear, the other day I was trying to hook up a new monitor, and the tangle of cables behind my desk was just uh, almost overwhelming.
Oh, I know that feeling. The dreaded cable nest.
Exactly. And we've all been there, right? With a rope or a string or,
Mm.
those old wired earbuds.
Mm.
But that moment, that really satisfying moment of finally untangling it, that's actually the heart of a whole field of mathematics called knot theory.
It really is.
And today we're doing a deep dive into maybe the most basic way to measure that complexity, the unknotting number.
It's a beautiful concept. It basically quantifies how much work you have to do to turn a complicated knot back into a simple unknotted loop.
So it's like a difficulty score.
Pretty much. The unknotting number is the minimum number of times you have to pass one part of the knot through another, what we call a crossing switch, to completely untie it.
A crossing switch. Now, just to be clear, that's not just like pulling on the ends of the rope, right?
No, not at all. It's a very precise topological move. You take one strand and you deliberately pass it either over or under another strand it was crossing. It's a concept that was first properly defined by Hilmar Wendt way back in 1936.
So our mission today is to figure out why this one simple number tells us so much
Yeah,
and, maybe touch on a pretty huge breakthrough that just happened.
sounds good.
Okay, so let's unpack this. I know there's a basic rule that the unknotting number can't be more than half the number of crossings in the knot. But let's use some real examples.
Absolutely, that's the best way. So if you take the most familiar knots, say the trefoil knot,
The one that looks like a sort of three-leaf clover.
that's the one, that knot, and also the figure 8 knot, which looks completely different. They both have an unknotting number of just one.
Just one move unties them.
Just one strategic flip, and they become a simple loop. But then you look at something like the 701 knot.
Right.
It's way more complex just by looking at it, and its unknotting number jumps all the way up to 3.
Wait a second. If the trefoil and the figure 8 look so different, how can they both have an unknotting number of 1?
And that's where the number reveals something deep about the knot's structure.
Okay.
If a knot has an unknotting number of 1, we know immediately that it has to be a prime knot.
A prime knot. Is it like a prime number, something that can't be broken down?
That's a perfect analogy, yes. It's like an atom in the knot universe. Any knot that has an unknotting number of 2 or more is probably a composite knot, something built by, tying those prime knots together.
I see. So the number helps us find the fundamental building blocks. That makes total sense.
Exactly. Before we get to the really big breakthrough, this might be a good moment to thank our sponsor.
Good idea.
This deep dive is brought to you by Silk. If you're dealing with your own complex problems, maybe in AI training, automation, or software integration, you need someone who can find that one key move.
Like a crossing switch for your business.
I like that. They uncover where new technologies can make the most impact. You can find out more at embersilk.com for any of your advanced AI needs.
All right, we're back. And finding this unknotting number, it's not always easy, is it? We know it for all the prime knots up to 9 crossings, but it's still ongoing research.
Oh, it's incredibly difficult in some cases. The unknotting number of the 10-dollar knot, for example, is still a complete mystery. It's an open question.
Wow.
But we're not flying completely blind. For some specific families of knots, we found these amazing shortcuts.
Like what?
Well, for any non-trivial twist knot, the unknotting number is always 1. Always.
Simple as that.
And for those really beautiful symmetrical knots, the torus knots, we have a perfect formula for it. P1, Q1, 2, 2. It just scales predictably.
Okay, this is where it gets really interesting for me. For decades, right, mathematicians were asking this one huge question. If you take 2 knots, knot A and knot B, and you tie them together, which I guess is called a connected sum, is the new unknotting number just A plus B? Was it additive?
Precisely. The assumption, and it's a very logical one, was that the total work to untie the big knot would just be the sum of the work for each piece.
It just makes sense.
It does, and a lot of theories about composite knots were kind of built on that assumption.
So, what was the answer?
Well, the resolution only came in 2025, and it was a huge shock.
No way.
The unknotting number is not always additive.
What? So what was the counterexample?
It's so cool. They found that if you take the 701 knot and you connect it to its own mirror image, the unknotting number of that combined knot was actually 1 less than the sum of the parts.
1 less. How is that possible?
It means that when you join a knot with its mirror, they somehow topologically cancel out a piece of each other's complexity. They help each other untie.
That is fantastic. It just shows that even in a field that seems so defined, there's always room for a discovery that just flips everything on its head.
Absolutely. It proves that math is a living, evolving thing. The
Yeah.
future of what we can discover is just wide open. And, the unknotting number is just one of many tools we use.
Right? There are others.
A whole toolkit. We have the crossing number, the bridge number, the linking number, even the stick number, all these different ways to quantify these amazing structures.
So what other surprising simplicity is just waiting out there to be discovered in those other numbers? It's definitely something to mull on.
If you enjoyed this deep dive, please subscribe to the show.
Hey, and leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.